Alright, folks, in this video we'll be talking about the pressure, the relationship between atmospheric pressure density and pressure density with the temperature, pressure density with the altitude with the other factors. So in this slide you are seeing that astronaut actually floating into the space. So the one question, normally in the normal situation, if we go out, we do not feel any pressure, outside pressure, but we know that our atmosphere is actually pressuring us 14.7 pound for each square inches. That's mean 1 inch, 1 inch, 1 inch, 1 inch. That's called square inch. So if you are looking at the column, this column, the molecule, the weight of the molecule is giving pressure onto 1 square inch of surface, 14.7 pound. So those are near the surface, the density of the air molecule are so much compact and that's colliding each other, and that's collideness creating atmospheric temperature little bit warmer. So we'll be talking in some extent about that. So normally, why don't we feel atmospheric pressure? Because we have atmospheric pressure and we also have the outband blood circulation pressure, and also inside our body we have atmosphere, we have air. So that's air and blood circulation actually reflecting back the same amount of pressure that is from the outside of the atmosphere. That's why we do not feel any atmospheric pressure. So what would happen if we go all the way to the mountain, somewhere 5,000 meters from the ground? We will feel lack of pressure. We will having some sort of breathing problem. So our nose may bleed. That would be the situation. If we go furthermore into the space, there is no air there and you don't have air pressure. So if you are not wearing any suits, what would possibly happen? Your vein in the body, your nose, vein, and everything will sprout out and your blood will be spreading all over the body. So that would be the situation. So a standard sea level pressure is 1013.2 millibar, and we'll be learning about the relationship between air pressure and density and with the altitude. So as we go up, that's mean from the ground to all the way to up, our air density decrease, air pressure decrease, and also into the troposphere our temperature also decrease. So all the relationship with altitude, the density, the pressure, and the temperature all are inversely related. So as you increase your altitude, you climb up, your pressure decrease, your density of the air decrease, and also temperature decrease. So temperature decrease we'll be talking separately in the adiabatic lab straight later on. So there are some factors that cause air pressure to change. Altitude. By the way, one thing, the difference between elevation and the altitude. So altitude means atmospheric height. Elevation means ground height. If you are considering to represent talking to your friend that you climbed in the mountain, you will say the elevation. If you are flying into the plane, you say altitude. That's mean atmospheric height, and this one is ground height. So this is the difference. And temperature. So earth rotational force also influence the pressure and regional air circulation. There are some things that we'll be talking later on. So we know normally the relationship between air pressure and density with the altitude, and will also with the temperature. Now, as we know that from the ground, if you look at this red line, it is telling you how much pressure you are decreasing with the altitude. So from ground 0 kilometers or miles, sorry, this is kilometers. So every 5.5 kilometers, if you go from the ground to up, you are losing 50% of your pressure. Then here you will lose 50% from the previous pressure. Every time if you go 5.5 kilometers above, or 5.6 give or take, you will lose 50% of your pressure that you had before. So this graph is telling you then an exponential, or you can say that logarithmic actually, that is telling you how much pressure that you have above, how much pressure that you have below. So density, there is equation for that. Density is equal to mass divided by volume. Pressure is equal to force divided by area. This is the relationship, so you have to remember that. What is density? So density always mass, total mass of the air divided by total volume of the air. So definitely if you go up, your mass is decreasing, the air molecule is decreasing, that's why the density is decreasing. Pressure, force, so all the atmospheric molecule is pressuring due to the gravitational force here. It's a much higher here. If we go up, it will decrease. This is the relationship. So this would take a little bit overview for you, how much pressure that you have above and below, that we already talked about that. I hope that you have a little bit understanding on that. Let's move forward. The real concern today. So vertical structure of the atmosphere. So this line, you have to look at that. Previously we know about the relationship between altitude and pressure and density. Now we'll be learning about the structure. So we have 4 atmospheric layers. First one attached to the surface is called troposphere. Then you have stratosphere. Then you have mesosphere. Then you have thermosphere. So in between 2 atmospheric layer, so this one is troposphere and this one is stratosphere, we have a boundary layer that's called tropopause. And then again, stratosphere and mesosphere, we have a boundary layer called stratopause. Then we have mesosphere and thermosphere, we have a boundary layer called mesopause. Okay, we'll be talking the details about that. So let's start from the ground to up. This is troposphere. So you have to bear in mind that all the atmospheric interaction that we see tornado, we see cyclone, rainfall, front system, cold front, warm front, thunderstorm, anything you see, that is all happening into this atmospheric layer. So that height is 0 to 11 or 12 kilometers above. We have cloud and the vertical cloud. We'll be talking about the cloud later on. So this line is telling you temperature either increasing or decreasing into each of the layer. So if you look at over here in the troposphere, your increasing altitude telling you that your temperature is decreasing. So that is happening here. Environmental lapse rate. The flat environmental lapse rate into the troposphere is 6.5 degree per 1000 meter. That's mean every 1000 meters you go above, you will lose 6.5 degrees centigrade of your temperature. So from troposphere, if you go up, your temperature is losing. The moment you are continuously going up here, the moment the temperature decreasing rate is stopped. That's mean with the altitude your temperature is now no longer decreasing, it is being remaining same, steady. That's mean this called tropopause. The moment it again with the increasing altitude the temperature is increasing. You see here that is stratosphere. So this is called temperature inversion. That's mean with the increasing altitude temperature increasing. It's supposed to be decreasing because this is troposphere decreasing, but into the stratosphere the situation is different. The reason is happening this one because the incoming solar radiation is colliding with ozone layer. So that's the important things. We know that we have an ozone layer into the stratosphere. This collision is ultraviolet radiation actually absorbed by the ozone gas. That's why this temperature increase. We may talk about that later on in details. So the moment if you keep going from here to here, that's mean the stratosphere and mesosphere in the boundary layer, the temperature is remain same. That's called stratopause. Again, mesosphere is acting like same as troposphere. That's with the increasing altitude your temperature decreasing. Then you have mesopause because temperature is not changing here. Then you have thermosphere. In the noon daytime in the thermosphere temperature actually increases significantly because they strikingly collide with the sun photon with the air molecule. It's actually strikingly increase. So the layer, boundary layer, the layer, boundary layer, layer, boundary layer, and layer. Okay, so in brief, tropopause, troposphere, with the increasing altitude temperature decrease, and then stratosphere with the increasing altitude temperature increase, mesosphere with the increasing altitude temperature decrease, then thermosphere strikingly increasing. So this is the fundamental of vertical structure of the atmosphere. So we have many things over here, and we know that northern light, aurora we find here thermosphere. So in the troposphere, this most important atmospheric layer because we have interaction directly on that. So environmental lapse rate, we'll be talking about that. This adiabatic lapse rate in another word we can see. So as we know that troposphere with the increasing altitude temperature decrease, but we have two types of situation. This is called from here to here. It's called dry adiabatic lapse rate. From B to D, this cloud means the air over here cloud is saturated. So in two different situation environmental lapse rate is different. So dry adiabatic lapse rate means 10 degree per 1000 meter. Every 1000 meter if you go above from the ground in the dry situation, your temperature you will lose 10 degree per 1000 meter. But when you are entering into the saturation situation, that's mean cloud or condensation is occurring from here, this rate is being changed half. That's mean 5 degrees centigrade per 1000 meters. So you have to remember all the time unsaturated rate and saturated rate is different. Now there is a calculation you can do that, but from D to E, that's called leeward of the mountain, from here to here, if you go down your temperature always increase because when you are going down your atmospheric pressure is increasing. That's mean air molecule inside is colliding more rapidly than previously. That's why this collision is striking each other, making heat, and that heat is increasing your temperature. So this is the fundamental reason that when you climb down from the hill or somewhere all the way to up, it is actually increase the temperature. So I hope that you have a little bit understanding about that. We'll be talking later on as the semester progress.